south.
No. I mean, I could, but I didn't. And even if I did, I wouldn't have noticed it was 2 to the 64 minus 1. That thought would not have occurred to me.
That's a distinct possibility at this point.
Does the arrows mean they're interchangeable, or you messed it up?
They're interchangeable.
Okay.
Does it
Actually,
natural
what
numbers?
it actually means, Christian, definition number 2 is my definition. Definition number 1 is your textbook definition.
Okay.
Does it have to be natural numbers though,
Yeah.
or would it be just numbers that share something in common?
No, so when we talk about real sequences, natural numbers. But when you talk about sequences and complex analysis, you allow it to be all integers. So it can be negative numbers as well. Now there are situations, since you brought that up, Christian, there are situations in which this can be extended to the whole number system. Do you guys know the distinction? The whole number system is just a natural number system with zero included. Yeah, that's the only difference.
I was thinking of your example of when you started with a half and then took that, multiplied it by a half and added it, and multiplied by a half and added it, until you, well, made it into a summation and got 1. So if it's only natural numbers, then that doesn't work as a
Fibonacci.
sequence. Yeah.
Yeah, very good, Christian.
That's what
I said it first.
Oh, did you?
True.
I didn't hear. Oh, we stole your thunder. Yeah, it's the Fibonacci sequence. So sorry, Jessica.
I got it.
Yeah, it's the Fibonacci
See,
sequence.
she backs me up. I just don't forget more.
Jessica, tomorrow for lunch, maybe we should pack it in a handbasket.
So you're just adding
It's like a picnic.
That's right.
one to the left.
So if I were to actually write down formulaically what the Fibonacci sequence is, it would be something like this. I guess we can start with 1. Well, I guess if we start with 1, this would be 0. Right? There we go. Yeah, and that's why you gotta allow yourself the whole numbers, because sometimes it's better to start with the index of 0. But again, what I'm looking at is viewing this as a function of natural numbers. So think of this as an f of n plus 1. You see that what this says is to get the n plus 1 term in the sequence, what you do is you add the 2 prior to that entry to get that in. So that's right. So that's an example of a sequence. These sequences come in all kinds of shapes, and well, they're all infinite, right? So I don't want to say sizes, but they have certain densities associated with them. We're only going to spend a little bit of time looking at sequences. Ultimately, what we want to do is look at series. The difference between the two is a series is what you get when you add up all the terms in a sequence. Right? So the sequence itself is nothing more than a list of numbers, and it's represented in a lot of ways. You can also represent it, let's say something like this. Sometimes that's the way a sequence is represented. They use curly brackets, because you usually use curly brackets for a set, so it wouldn't be unreasonable to say that this is, let's say, the set F or Fibonacci numbers or something like that. But sometimes we just define it in terms of the generator. So this is the thing which generates, this is the one that Christian was talking about earlier. Remember when I did the box, and I took a half, and then a half of a half, and then a half of a half of a half? That's what would generate this sequence. Because if you start listing this out, and so if there's no indication as to what n is, you can assume it's a natural number. So that's a safe bet with sequences. So this is really the sequence is like a half, a fourth, an eighth, a 16th, so on and so forth.
So you would start with 1 and not 0.
Usually. There are going to be situations, especially when we move in a series, there are going to be situations where we start with 0. Well, what you're not going to see is a negative index in any of this. Well, what I was saying to Christian a few minutes ago was that if you take a class called complex analysis, then we do what we call Laurent series, and those are defined from negative infinity to infinity instead of just 0 to infinity. Yeah, So they do exist.
Couldn't you technically end that series or sequence with 0?
Well, and that's essentially what we're going to be talking about. It's not that you can end it with 0 as much as
1 over infinity.
what the limit is equal to, right? In other words, what Christian is pointing out here is that the limiting value is 0, even though 0 itself is not contained in the set of numbers. So you could write out all infinity of those numbers in the set, and the point is to get closer and closer and closer to 0, but never actually get to 0. But the limit of the sequence is in fact going to be 0. So a good part of what I'm going to talk about for the sequences tonight is probably the first half or maybe 2/3 of the class or so, is trying to establish the limits of sequences. And there are a couple of ways of doing that. The easiest way to do it is to simply replace the n with an x and just go at it that way. You can't always do that, but one of the reasons, we can use this notation as a shorthand, but recognize there are some difficulties with viewing it this way. Because since n is a natural number, there's no space in between the numbers themselves. In other words, in a natural number system, what comes after 7? The answer is 8. So as soon as you start talking about a limit, the assumption is that you're in this continuous regime where you can, flow from one number to the other. Whereas in sequences, if I were to plot this, I guess what I'm saying is if you plot a sequence,
Get a bunch of points.
you get a bunch of points. That's right. You don't get a continuous curve. So all of a sudden, when you start talking about the limit, it's kind of weird because you can't really go in between those points per se. So one of the theorems I'll introduce soon is simply replace the n with the x and then take the limit that way. The problem is there are situations where you don't have an analogous form for the x's. In other words, what if you had an n factorial in here? What do you guys know about factorials?
They get infinitely long.
So,
You can't derive them.
Okay. So a factorial is only applicable to what kind of numbers?
Integers.
Integers,
Whole
or
numbers.
natural numbers actually, or we can define them for negative numbers, but they're naturally defined for natural numbers. They're normally defined for natural numbers. So you can't, for example, replace it with an x because x factorial is not defined. What is 0.7 factorial? Well, it's not defined for those fractional values, right? So there are some issues that have to be dealt with. But before we get to that, I want to practice just trying to do some pattern recognition here. So that's an important skill you guys are going to have to pick up.
What is diagrams?
Pattern recognition.
Pattern recognition.
I have to recognize patterns.
Patterns. Yeah. That's,
It's not like it's in the word.
But that's hard.
You did well in the FCAT, didn't you?
Yeah.
You'll be fine.
That did not have calculus on it.
It had patterns.
well, this is not technically calculus either, Luciano. What I would like you guys to do is come up with a generating function for that sequence.
I got it.
All right. Go for it.
You're just multiplying the number by negative 2/3. So
How would we express, so that would work as a description if we were doing this recursively.
yeah,
Because you could say multiply the last one by whatever it might be. But I'm looking for a closed form representation so that if I wanted to figure out the 8th term, I could just plug in n for 8 and get an answer. And you see, that really is the nuance in my definition versus, they're equivalent definitions, but to view it as a function who's defined on a set of natural numbers is a little bit more instructive because then you can plug in 100 without having to calculate the first 99 of them. Right?
so negative 2/3 raised to the n power where n can start at 0.
All right, there we go. Well, I'll just say it goes from 0 to infinity, right? Up to infinity. So it's actually a better way of saying it would be a whole number, right? And in fact, since we don't really have a symbol for the whole numbers, a better way to represent that would be a natural number together with the 0 element, right? That would be a good way of
Shouldn't you do it 3/2 times negative 2/3 to the n? And then you can start with 1.
Then you start with 1, and that's so you're starting to see there's no unique representation for this, right? That's absolutely right. Right, so yeah, if you want to start it from 1, it's just going to be an index shift, and you're going to get an extra factor of say 3/2 out there, make it an n minus 1 or something along those lines. So part of it, and I'm not gonna dwell on this because obviously